So as we come to the first examples that you're going to have out of 11.2, I'm going to do a bunch at the same time because your book's really wise. As I start you out in the homework, and as the book starts you from 25 to 36, they're doing something great. They're saying, what are you going to conclude in the end when you're done doing all these row operations and get it into this row echelon form where you have ones along the main diagonal and zeros underneath? Are you going to be able to read your answer? And so I thought I would show you that, yeah, it's pretty easy to read it. And so although I'm listing out numbers 28, 30, 34, and 36, I'm going to go through them in a different order. I'm actually going to start with 36 because 36 is a good example of just reading an answer. If you notice in 36, there's lots of zeros. They call this reduced row echelon form. It's not an expectation, but if you get it into this form, you can totally read your answer. So take a look at the first line. Notice what we have in this one. We have 4 variables. And so sometimes they'll use x, y, w, and z, but most of the time they'll use x1, x2, x3, and x4 once they get above 3 variables. And so that'll happen a lot. You'll be in a business class or a business situation really, and you'll realize you have way more than 3 variables going on. And so this is simply read. Take a look at this very first line. As we look at that very first line, let me get a different colored pen in here. Let me underline it in blue. That very first line tells us that x1, the only one living, is 1. The second line, which I'll put in green, tells us that x2 is equal to 2. The third line, which I'll underline in red, tells us that x3 is equal to 3. And the very last one, which I'll underline in yellow, is telling me that x4 is equal to 0. And so we get a very nice answer out of this. We get the ordered pair 1, 2, 3, 0 as the point of intersection. So sometimes it's listed like that, and sometimes it's just listed out the way I have it on the left-hand side. Either way is okay. But that's an example where every variable is accounted for, but other things happen. Take a look at 34. Look how many variables it has. It has 1, 2, 3, 4 variables, but only 3 equations. That's going to happen sometimes in practical applications, is that you have more variables than you have equations, and so therefore one of them can kind of be anything. But let's take a look at what's being said here. If we go from the top, it tells us x1 is definitely 1. It tells us x2 is definitely 2. And the last one says that x3 plus 2 times x4 is equal to 3. So the way this is typically handled is to solve this last one for x sub 3 and realize that that's 3 minus 2x to the 4th. And so the answer will be this. The answers will be written often like this: x1 is 1, x2 is 2, x3 is 3 minus 2x sub 4, and x sub 4 can be anything. Now think about that. If you pick something for x sub 4, like 2, it would totally unlock what x sub 3 is, and you already know x sub 1 and x sub 2. So it really does depend upon what x4 is. You could make the argument that you could solve for x sub 4 and let x sub 3 be anything. There's no difference between that. You're just picking whichever variable is free to roam. So there wouldn't be anything wrong with letting x3 be the one that could be anything, and then x4 be determined by that. And then 28. 28 is an example where if we look at the top line, it says x1 is equal to 0. Then it says x2 is also equal to 0. But take a look at the last one. It doesn't say x3. It doesn't have any x1s, no x2s, no x3s. So really 0 is coming out on that side is equal to 2. This is a non-true statement. It can't happen. And so this is where we get what the book will call an inconsistent solution or a system, or basically what we used to say is it has no solution. Either way you write that to me is great, but that's how you're going to recognize a no solution case. And then giving you one where there's 3 equations and 3 unknowns. Here's a situation where that last row is all zeros. This is more of what what a row echelon form would look like. We tried to get a 1 in the bottom and we couldn't get it. And so look at what we're seeing. We're seeing that x1 plus 4, well, you know what? With 3 variables, let me take that back. With 3 variables, I know what they're going to do. They're not going to call them x1, x2, x3, because they're going to call them x, y, and z. Let's do that. They're going to say x plus 4z is equal to 4. And then we know y plus 3z is equal to 2. And take a look at what's last. 0 equals 0. That's a true statement. Now notice what you have. You have an ability to express x in terms of z. You have the ability to express y in terms of the same z. So z is the thing that can be anything. And you would unlock the other two. So if you pick a z is equal to 1, then you'll have your system. You'll have a solution to that system. This is the example of an infinite amount of solutions. And those solutions would all be generated by letting z be anything you can dream up. And then x and y are completely determined. And it would solve all 3 of those equations. So they were wise, I think, in giving you the results of what could work out as you go through this form. You could get a unique solution. I think that'll happen most often. You can get something where there's an infinite amount of solutions, where you can pick anything you want for x4 and then the other ones are unlocked. 28, you could get something that has no solution. And then 30, you can get an infinite number of solutions, not because there's more variables than equations, but just because there's just a lot that can work.